Good afternoon. We are continuing with our college algebra lectures. This is lecture 2. We are using as a guide the OpenStax College Algebra 2nd edition. We are in chapter 1, section 1.1, if you're following along with that. If not, otherwise, we are doing today the order of operations, PEMDAS, the properties of real numbers, which includes the commutative properties, associative properties, the distributive property, and then the additive multiplicative identities, additive and multiplicative inverses. And then we'll look at algebraic expressions and simplifying algebraic expressions. Seems like a lot, but it should go rather quickly, I think. So let's start with the order of operations. And this should all act as a review before we get into the actual meat of the college algebra lectures. So this mnemonic that most of you have probably heard, the PEMDAS. In the PEMDAS, we have the parentheses. We can also think of them as brackets. They will be like that. Exponents. Multiplication and division, and addition of subtraction. So this is the order in which we do arithmetic. All right, so quickly, before we start, let's look at a quick exponential. So an exponent, we have a base b and an exponent x. B is the base. And we say what it's raised to, we say it's the power. All right, so 2 squared, the base is 2, the power is 2, and this relates to multiplication in this fashion. We multiply the base however many times of the power. So 2, we multiply 2 times. So we have 4. Another example is x to the 4th. That means we multiply x 4 times. We will go over exponents, I think, in lecture 3, a little more in detail, but for now, this should be sufficient. All right, so the order of operations, I'm going to assume that you know arithmetic. I'm going to assume that you know addition, subtraction, multiplication, and division. So when we look at examples, I'm not going to explain that arithmetic. So let's just look at the order of operations really quick in an example. And again, this is sort of the preliminary chapter of a college algebra textbook where we get familiar or refamiliarize ourselves with some of the things prior to a college algebra course. Some courses might skip these things. And if you're looking at these lectures, you could probably skip to, I'm guessing, chapter 2, which will be the core of the beginning of the core of the college algebra course. So, but if you need these preliminary refreshers, these are good. That's why I'm doing these. So, example, let's write 25 plus 7 times 3/4 minus 6 squared. So we're applying PEMDAS. And the mnemonic, obviously, parentheses, exponents, multiplication, division, addition, subtraction. So we notice there are no parentheses here. So we don't have to worry about the parentheses. Exponents. I see there's a 6 squared. So we will begin by squaring 6. And we keep the sign out front. So negative 36. There's something to note. I see this commonly with students. 6 squared, negative 6 squared is negative 36. However, negative 6 quantity squared is equal to 36. The reason is this is really just -6 times 6, whereas the second one is -6 times -6. We know that negative times a negative is a positive, so we get 36. And this is 36, and we hold on to the negative. So that's why the 6 squared is negative. If it was quantity 6 squared, -6, then it would be positive 36. All right, so that's the exponents. Now we look at the multiplication, and we do the multiplication and division left to right. So whatever comes first, moving left to right. So the first thing we see is we have 7 times 3/4. So we can think of this as 7 over 1 times 3 over 4. We multiply the top, and when we multiply the bottom. So then we get 21/4. So let's put that in line here. So I should write equal signs. So 25 plus 21/4 minus 36. Now we look for any more division or multiplication. We don't see any. So now we do addition and subtraction left to right. So the first thing we're going to look at is the 25 plus 21/4. So we need a common denominator, add fractions. So I'm going to write 21/4 over here. And to get a common denominator, we essentially have 25 over 1. So if I multiply the top and the bottom, I'm going to get 100 over 4 plus 21/4. This again allows us to have a common denominator of 4, and then all we need to do is add the top of the fraction. So 100 plus 21 is 121. So 25 plus 21/4 is 121/4. So let's write that 121/4 minus 36. Now you guessed it, we're going to find a common denominator between 121/4 and 36, which means we're going to take 36 over 1 and multiply it by 4 over 4. That gives us 121 minus 144. And then we have a common denominator of 4. And 121 minus 144 is -23/4. So with the order operations, what we get is -23/4. Let's do another example real quick, a little more complex. The square root of 5 squared minus 4 squared plus 19 times 7 minus 6 quantity squared. PEMDAS, so we're going to look for parentheses first. So we see we have a parentheses here. So I'm just going to subtract 7 and 6, which leaves us with 1 squared. Now we have an exponent. We have this squared. This technically is an exponent. We'll get to that in the exponent section, but the square root is a rational exponent. But let's think of this too maybe as a quantity. It's underneath the square root. So we have 25, that's 5 squared, minus 16. 1 squared is just 1. Now let's evaluate the square root. 25 minus 16 is 9. Now we could evaluate the square root. The square root of 9 is 3. 19 times 1 is 19. So that was the multiplication and division. So we did the exponents, multiplication, division. Now we're going to add. So that is 22. All right, simple enough. Order of operations. PEMDAS is always a good way to think about that. This will always be true in algebra. There'll be cases and logarithms where we might expand or contract. We might look at the order of operations again a little more closely, but that's a ways away. All right, so now we're going to look at what's called the properties of the real numbers. In lecture 1, we looked at the real numbers and we built them up by looking at whole numbers, natural numbers, integers, rational numbers, irrational numbers. Here we're going to look at some of the properties of these. The first one, and again, this should all be somewhat review. We'll call this a commutative property of addition. So this is something that the real numbers have. And what we mean by that is that I can add, I'm using variables here, in any order. X plus y is the same as y plus x. A simple example of this would be if I take 4 plus -6, is that going to be equal to -6 plus 4? I'm just rearranging the order in which we're adding. So this is -2, and this is also -2. So we see that addition is commutative. Commutative, this means that we can add in any order. So we have also a commutative property of multiplication. And we use variables. Let's say x times y, it will be the same as y times x, meaning the order in which we multiply things shouldn't matter. Now, if you move on from college algebra to, say, linear algebra, you'll notice that if we multiply matrices, that it's non-commutative in some cases. So assuming that something is commutative is a mistake. Let's look at an example. 2 times -6, is that the same as -6 times 2? Well, we get -12 equals -12. So yes. So again, this is commutative, addition, and multiplication. Now we're going to have association, or the associative property. And we're also going to have addition and multiplication. And this, let's use different variables, a plus b plus c. Now, if I group them this way, will this be the same as if I group them this way? So the associative property says that we can do that. And from your order of operations, we know that in the left-hand side, we would do a plus b first, and the right-hand side, we would do b plus c first. So let's see if that's actually true. So an example, let's say 2 plus 3 quantity plus 4, is that the same as 2 plus 3 plus 4? Now remember PEMDAS. So we're going to add 3 and 5, or 3 and 2, which is 5, plus 4. And then we're going to add 3 and 4, which is 7. 5 plus 4 is 9. 2 plus 7 is 9. So yes, these are the same. Even though the steps look like we're coming to a different conclusion, the real numbers are associative under addition. And I'm using really good examples. And so far I'm just using integers so as not to overly complicate. And the real numbers are also associative under multiplication. So let's say we have x times y times z. Not a question mark. This is a statement. This is true, that it's the same as x times y times z. So this is a fact. We can associate multiplication however we want in the real numbers. So an example, simple one, is 2 times 3 times 8. Is that the same as 2 times 3 times 8? Order of operations, we do parentheses first. 2 times 3 is 6 times 8. This is 24. 6 times 8 is 48. 2 times 4 is 48. So yes. So No surprise, that checks out. Those are pretty clean, quick examples. Now let's look at something that we use a lot in solving equations and in simplifying expressions, called the distributive property. And the distributive property says that if I have a number, a real number x, and I multiply it by the quantity of some sum, this will be equal to x times a plus x times b, meaning we distribute x through the addition. So an example, again, we're doing essentially this. We're multiplying x times a, and then multiplying x times b, and then we're adding those two. That's how we get the right-hand side. So let's use another simple example. Let's say 2, 5 plus 7. Is that the same as 2 times 5 plus 2 times 7? That is 12 times 2. This is 10 plus 14. So 24 is indeed 24. So you can see this distribution works fine. These are simple cases. As we get through the course, we will have a little more tricky things distributive-wise. Remember, FOIL is a form of distribution, if you've done foiling before. If you multiplied long polynomials, you've done another form of distribution. I want to talk about a special case before we move on. So notice that x minus y is the same as x plus negative y as a fact. So let's look at something like x minus 5 plus 3. Now, the order of operation says we do the parentheses first. We can add 5 and 3, which is 8, and then take 12 minus 8 will give us an answer. We could also think of this using the distributive property, and we can say, well, what we have, this negative is the same as negative 1. And so 12 plus negative 1 times 5 plus 3. And why are we doing this? It's sort of convenient because now I'm going to distribute negative 1 via our rule. What I mean is convenient is if we have a quantity of variables and a number outside, we can distribute. If there is no number and it's a subtraction, then we can distribute that subtraction, so to speak, in the form of negative 1. And then I get negative 5 minus 3, and that is minus 8. So now we have 4. So the distribution property with a subtraction of a quantity can be the same as distributing that negative, that subtraction through the quantity, which in simplifying or condensing things will be a little bit more straightforward and interesting once we get to that part. All right, so now we are going to talk about a couple identities. And again, these should be familiar. These are sort of a more rigorous way to think about things you already know. So identities, this is, let's say this is a definition. So we have something called the additive identity. We define this as there is some unique real number, which we're going to call 0, such that for any real number x, x times 0 is equal to 0. So it's a fancy way to say that we have an identity element called 0. Oh, I'm adding. I'm not multiplying. We have an identity element 0 for when I add 0 to anything, I get that number back. Meaning 2 plus 0 is 2, 3 plus 0 is 3, and so on. The additive identity meaning I get back what I started with. Now we have a multiplicative identity. And we can think of this as a definition as well. This will be, again, a unique real number called 1, such that for all x, for all real numbers x, x times 1 is equal to x. Unique meaning there's only one of these. There isn't two multiplicative identities. There isn't two additive identities. The only ones that are additive and multiplicative identities are 0 and 1. So again, 2 times 1 is equal to 2. 3 times 1 is equal to 3. The identity part means that we apply this in multiplication of 1, we get back the original number. That's what we kind of mean by identities. Okay. We're going quick, but I think most of you should have seen this at some point. So let's look at additive inverses. This should be another definition. I'm not spelling too well. So additive inverses, which means by definition for every single one, every single real number, we'll say x, every single real number x, there is a unique real number, which will be denoted by, I should say denoted by 1 over x, reciprocal, right? These are called reciprocals. Oh, I'm doing the multiplicative, so let me just change this. This is a multiplicative identity. Inverse myself. Such that 1 times 1 over x is equal to 1. That is the multiplicative inverse. So every real number with one caveat, that x is non-zero. So 0 does not have a multiplicative inverse in that sense by this definition. So every non-zero x. So 2 times 1 over 2 is 1. 3 times 1 over 3 is 1. Square root of 2 times the square root of 1 over the square root of 2 is 1. So no matter what real number you give me, I have the reciprocal and the additive inverse. Now, you might think, well, what if I have 1/3? What's the reciprocal of 1/3? Technically, it's 1 over 3, which is the same as 1/3 times 3, which is 1. Everything has a reciprocal except 0. So the next is what I wrote out but didn't complete. It's additive inverse. So again, for every real number x, there is a unique real number and we're going to call this negative x such that x plus negative x is equal to 0. These are additive inverses. And in the case of additive inverses, what we get is the additive identity. In the multiplicative inverses, we get the multiplicative identity in 1 and 0. So yeah, anything times anything plus itself plus its inverse. So 2 plus negative 2, obviously it's 0. Square root of 2 plus its negative is 0. So these always exist. The reason we include 0 is it's sort of redundant, but negative 0 is 0. 0 plus 0 is 0. So technically 0 has additive inverse. So those are the properties of real numbers that we will use throughout the course, throughout every college algebra course. Now let's look at something called algebraic expressions. Algebraic expressions are a collection of numbers, variables, operations, such that there isn't an equal sign. An expression, let's give us some examples. X squared plus 2x is an expression. The square root of 3x to the fourth, y to the third is an expression. X to the third plus 4 is an expression. If I put an equal sign, that's an equation. So expressions lack the equal sign. So the couple things we need is we have x's and y's in here. So we call these variables. X and y are variables. And the constants here, it might not seem obvious that this exists here, but 1's a constant, 2, 3, and 4 are constants in these three expressions. The reason that 1 is here is because we always think of 1 existing in front of a variable if there isn't anything in front of the variable. So the coefficient of just x to the third is 1. For instance, 2x squared, the coefficient is 2. That's another expression. So in the book we're using as a guide, there are some problems in this section that ask you to look at expressions and classify some of the elements in there. So you can give that a shot and see if it makes sense. Let's evaluate some expressions. So we're going to take some random expressions. So example, x squared plus 2x plus 1. So it's an expression. There's no equality. X is variable. 2 and 1 are constant. So, but we can find the value of this if we're given some value for x. So let's say, suppose x is equal to 0. Well, I'm going to replace x in this expression with 0 and then perform the order of operations. Exponents, parentheses. You don't have to do these in steps. You can do them at the same time as long as you don't violate the order of operations. So I'm squaring 0. I'm multiplying 2 and 0. So that means that this expression is equal to 1 when x is 0. We can also pick another number. Again, I'm picking really nice numbers. You can challenge yourself if you want by picking something a little more ugly. So this would be 2 squared plus 2 times 2 plus 1. 4 plus 4 is equal, nope, plus 1. I don't know why I wanted to get rid of 1. is equal to 8. I'm doing left to right, order of operations, 9. So when we evaluate this expression, when x is 2, the expression is equal to 9. Not too bad. Here's something you could try. Try x equals the square root of 2. Put the square root of 2 in there and see what you get. Okay. Let's try one more. Just a different look. So example, y plus 4 divided by y, let's say y squared plus 1. So this is an expression, there's no equal sign. So suppose that y again is 1. Well, I'm just going to replace in the expression y with 1. Now I'm going to do the top. 4 plus 1 is 5. The bottom, I'm going to do the exponent first. 1 squared is 1 plus 1. So we get 5 halves. Again, you can challenge yourself, pick a different number, pick something ugly. You could pick something like y equals pi divided by the square root of 3. Chug that in there and see what happens. Probably won't simplify very much, but you'll get a number. This will be a number. These aren't variables. Pi over square root of 3 is not variable, so you'll get something. So it leads us to the last topic for this video, simplifying algebraic expressions. So we're going to use the properties of the real numbers that we went through earlier, of course, arithmetic, to simplify some expressions. And expressions, again, are short little mathematical statements without equality. So let's look at an example. Here's an expression, 9 times x plus 8 minus 27. So we want to simplify this. We could just plug in values of x if we wanted to and find what the value would be. Or in this case, we can simplify it first, and then we have something that maybe looks a little bit better. And it's a little bit easier for us to manipulate once we're given values of x. So I'm going to use the distributive property first. That says that if I have the number out here times some quantity, I distribute the 9 to each term. So that's 9. I'm going to use parentheses to denote multiplication. 9 times x plus 9 times 8. And I'm going to leave this minus 27 out here. So left to right, I'm going to do the multiplication first. So we get 9x. And then we get 9 times 8 is 72 minus 27. So notice that 9x and 9x, the only difference here is I remove the parentheses. It's a lot easier to read this way. So 9x plus 72 minus 27. So then we get 9x plus 45. So we didn't evaluate, we just simplified. We just made the expression look better. And if you see, like these two things are the same, but one is simplified. One seems a little bit more straightforward. If I want to plug in values for x, it's simpler on the left than on the right. Let's try something a little bit more complex. Again, I'm just going to use integers. So we have 9x plus 4x times 2 plus 3 minus 4 times 2x plus 3x. So to simplify, here we can distribute, we can do order of operations. We notice the parentheses, again, PEMDAS. We have like terms in the PEMDAS, in the parentheses, because 2 and 3 are the same kind of term. 2x and 3x are the same kind of term, so we can add those. So I'm going to add those. That'll be 5 minus 4. 2x plus 3x is 5x. Now, order of operations says we do multiplication left to right. Nothing we can do for 9x, but we can multiply these guys. So 4x times 5 is 20x. I'm going to assume you know how to multiply, again, variables with constants. If you should need that assistance, tell me in the comments, and I can do a short video on how to multiply with variables and add variables in like terms, but hopefully that makes sense to you. 4 times 5x is 20x. So we see that the 20x minus 20x, this gives us 9x. So this long, ugly expression is really just 9x. That those two terms on the right there drop. And of course, if we replace x with some number, the bottom highlighted version is much easier than the top one. If we want to evaluate these expressions for any value of x. Again, try this. Put in x is equal to the square root of 2 over 3 and see which one is easier to do. Obviously, the bottom is going to be the easiest. If you're curious of what that would be, it's 9 times the square root of 2 over 3, which is equal to 9 square root of 2 over 3. And 9 divided by 3 is 3, so this is 3 square root of 2. Simple. All right, so that ends this lecture. All right, end. Next time, lecture 3, we're going to dig into exponents. More detail, some of the exponent properties, how to manipulate exponents, how to add, subtract, all that great stuff. So look out for that. Thank you for watching. Like and subscribe if you can. It helps us out. Have a great night.